Welcome. In this video, we're going to talk about molecular shapes. VSPER, as it's commonly referred to, is an idea or a model that the VSPER stands for Valence Shell Electron Pair Repulsion Model. And it's basically just what it sounds like, as confusing as that is. It just is saying that electron pairs out in the valence shell, the outer shell, repel each other. And because of this, we can predict molecular shapes. And it's a big deal to know what the molecular shape is because the molecular shape will determine physical properties like boiling point and viscosity, how thick it is, how easily it flows. And it also determines chemical properties like reaction rate. So knowing a molecule's shape allows chemists to predict and change that molecule's behavior. So a lot of catalysts and enzymes that are used to speed up reactions or inhibitors and preservatives that are used to slow down reactions, those are created by finding a way to change the shape of the molecule. So lots of pharmaceuticals, lots of products depend on being able to know and change the molecular shape. So the VSPER assumes three things about all molecules. It assumes that all electron pairs repel each other. That's because electron pairs have negative charges on them. And a pair then has one spinning each direction, but by the time you have those negative charges and then try and bring opposite spins in, more than one of the same spin is really going to create repulsion. So electron pairs are going to repel and have maximum distance between them. And I like the analogy they use of balloons. If you were holding two balloons by the end, by the part where you tied them, they would just naturally repel and have maximum distance between them, whether you had 2, 3, or 4 balloons. The second idea is that lone pairs take more space since they don't need to be close to another orbital for sharing, and there's only one nuclei holding that lone pair in place. They are going to spread out a lot more than the bonding pairs. So lone pairs repel more than shared pairs do. In other words, they take up more space, or you can think of lone pairs as being bigger balloons. And then bond angles are formed by the two terminal atoms, that's the outside atoms, and the central atom, and it's these angles that determine a molecule's shape. So most molecules will have 4 pairs attached to the center atom, and they can be shared pairs or lone pairs. The shared pairs could be single bonds or double bonds, but there should be 4 pairs of electrons around most center atoms. So then to use the VSPER model to figure out the shape, you need to know how many total pairs or bonding sites are attached to the center atom. And I tend to call them bonding sites because a double or triple bond is still only one bonding site, even though it has 2 or 3 pair. You can think of it as just being one pair or one bonding site. And then once you know how many total pairs are around a central atom, you need to look and see how many are shared pair and how many are lone pair. And then this is the chart we use. If you have just two pairs attached to the center atom, and they're both bonding pair, well then those two atoms attached to your center atom are going to get maximum distance apart, and it's going to be linear. If you have 3 atoms attached with no lone pair, they're going to get maximum distance apart, and it's going to be what we call trigonal planar. If you have 4 atoms attached with no lone pair, they're going to get maximum distance apart, and it's going to have this tetrahedral shape. What changes things up is when you have lone pairs. If you have 2 things attached to the center atom and suddenly you have 1 or 2 lone pairs, now you're going to have a bent shape like we have down here on the 5th one. And so that bent shape would be true whether there is 1 lone pair or 2 lone pairs attached along with the 2 other atoms. And likewise, if you have 3 atoms attached but you have a lone pair, instead of being trigonal planar, it is going to get, those 3 attached atoms are going to get pushed closer together, and we're going to call that shape trigonal pyramidal. The 6th and 7th one here, we're not going to worry too much because those are what we call expanded octets, and so those aren't common molecules that we'll be dealing with. Hybridization is the other thing that comes up, and we're not going to spend a lot of time on hybridization because it's not important to what we're doing, but the idea is that S and P orbitals are such different shapes that when atoms bond, the orbitals being used blend or mix together. They combine. So when you have an s orbital on one atom combining or bonding with a p orbital on another atom, they're going to morph their shape or change their shape, and that's what we call a hybridized shape or a hybridized orbital. So you form new identical hybrid orbitals, and since most atoms use 4 orbitals, they're going to be using 1s and 3 p orbitals to form those 4 bonding pairs. And so new hybrid orbitals called sp3 are developed instead. But if you have multiple bonds or if you have incomplete or expanded octets, then you might only use 2 orbitals. So you'd use 1s and 1p, and we call it an sp hybrid orbital. So here's the examples of hybrid orbitals. On my first one with CH4, I'm using 4 orbitals. So I'm using an s and 3 p's, so that's cleverly called an sp3 hybrid orbital. On my second example, NH3, I'm still using 4 orbitals, even though 3 are for bonding pairs and 1's for a lone pair, so that's still an sp3. But with BF3, because boron's not big enough to accommodate a double bond and there's not another lone pair, only 3 bonding sites are used, so we call that an sp2. And with carbon dioxide, only 2 bonding sites are used since they're both double bonds, so that's just an sp hybrid orbital. And I gave one example of an expanded orbital, and once you've used the s and 3 p's, you're going to have to expand into the d orbital, so that's called an sp3d orbital. And there's no need for you to memorize these because they're on the chart that you'll be using to determine shape. So let's look at a few examples. Determine the shape of CH4 and give the name of the hybrid orbital that will form. So CH4, I've got 4 electrons from the carbon, and I've got 1 from each hydrogen, so I've got a total of 8 electrons. So if I put C in the middle and attach the 4 hydrogen, each hydrogen is satisfied with its 2 electrons, the 1 shared pair. The carbon has got 4 pair around it, or 8 electrons, so it's satisfied. And I've used 8 electrons, so that is the correct bonding for it. And so if I think about it, I have 4 atoms attached and no lone pair, so those 4 atoms are going to spread out equally, and this is going to have a very symmetrical and tetrahedral shape. And so because it used 4 bonds, the s and all 3 p's orbitals, it's going to be called an sp3 hybrid orbital. NH3, I've got 5 electrons from the nitrogen, 3 from the hydrogen, so I've got a total of 8. And when I draw this, when I put the 3 hydrogens on, the hydrogens are satisfied, but nitrogen needs another lone pair. And when I count up, once again, I've used all 8 electrons. So this is the correct Lewis diagram for NH3. So what is the shape of that? Well, if this lone pair was another atom, it would be tetrahedral, just like CH4. If there was no lone pair, then the hydrogens could spread out equally and be trigonal planar. But because there is a lone pair, those 3 hydrogen are going to get pushed closer together, and it's going to be called trigonal pyramidal. SCl2, sulfur has 6 electrons. The 2 chlorine each have 7, so I have a total of 20 electrons. So when I put the S in the center and attach each Cl, I would need 6 more electrons on each Cl. I'd need 4 more electrons on the sulfur. And when I count up, that would take 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons to form that. So even though I've drawn it to look very linear, when I think about it, I've got 2 atoms attached and 2 lone pair, and really those 2 lone pair are going to push those 2 chlorines closer together, and so this is really bent. And my 2 diagrams mean the exact same thing, it's just a matter of what angle you're looking at it from. But because there's 2 lone pair, I know those 2 Cl can't stay maximum distance apart, so this is definitely going to be a bent molecule. But it's still going to be an sp3 hybrid orbital because I'm still using 4 different bonding sites, 4 orbitals. BF3, I've only got 3 electrons from boron. I've got 21 from my fluorine, so I've got 24 electrons. So when I put B in the middle and attach the 3 fluorines, They're each going to need 6 more electrons, or 3 pairs. And boron needs 1 more pair. But when I do that, I've now used 26 electrons. So when you overuse electrons, this is usually my clue to form a double bond. But boron can't form a double bond. It's too small. So if boron can't form a double bond and I only have 24 electrons, boron's just going to have to be incomplete with just 3 bonds attached to it, 3 atoms attached to it. And because of that, these 3 fluorine atoms will spread out maximum distance, and this will be what we call trigonal planar. And because it only used 3 bonding sites, this is an sp2 hybrid orbital. CO2, I've got 4 electrons from the carbon, 6 from each oxygen, so I've got a total of 16 electrons. So when I bond the oxygens on with single bonds, each oxygen still needs 6 electrons, the carbon still needs 4, and when I count up, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, so I've overused by 4, which means I need 2 more bonds. Well, that's no problem. Carbon can form a double bond, so if it forms 2 double bonds, 1 on each side, then what I need to realize is this oxygen only needs 2 lone pair, or 4 more electrons. This oxygen only needs the 4 extra electrons, or lone pair. And this carbon has all of its electrons being shared, so it's got 4 bonding pair around it. So that's my correct structure. And because I only have 2 bonding sites with no lone pairs, this will be linear. And the hybrid orbital will just be sp. And the last example I have for you is H2O. I've got 2 times 1 for the hydrogen, and 6. I've got 8 electrons to use. I put the O in the middle because hydrogen's always a terminal or end atom since it only forms 1 bond. So I've got 2, 4 there. I need 2 lone pair to fill it out. That takes 8. So this is my correct structure. And again, even if I had drawn this to look linear, like so, because there's 2 lone pair, I know this is going to be a bent-shaped molecule, and it's used 4 orbitals, so it's still an sp3 hybrid orbital.